So we were discussing Lebesgue integration theory, and our progress so far is as follows. In the ground level, which I call level 0, we have defined integral of a non-negative simple function. So let me remind you that if phi is a non-negative simple function, say phi is of the form summation alpha I chi bi, I is equal to 1 to n, without any constraint that alpha I should be distinct, beta I should be disjoint, etc., etc., we can define integral over phi dm as summation alpha I measure of bi. I is equal to 1 to n. And if you are interested only on integral over a measurable set E, then we can define it using integral over entire R via characteristic function. Note that the non-negativity constraint or restriction is imposed in order to avoid infinity minus infinity and so on. So if you are sure that measure of each BA is finite, we don't mind even if phi takes negative values. Is that okay?
Yes.
Yes, sir.
Now level 1 is as follows. That's what we were discussing yesterday. We want to integrate more general function, not just simple function. Okay. We started with a bounded measurable function. Let f be a bounded measurable function defined on a measurable set E and we assume that measure of E is finite. Then we have seen that integral of f over E can be approached in two ways. Okay. Integral over E f dm is equal to, right now we know only to integrate simple functions. So you integrate those simple functions which are less than or equal to f, phi simple, and then take supremum of all such integral. So you are underestimating the required integral and you are making the underestimate better and better. Or you can always do this, also do this in the following manner. You integrate simple function psi where psi is greater than or equal to f. We know how to integrate simple function. So this is overestimate for the required integral and make this overestimate better by taking infimum. And we have seen that Due to the condition that f is measurable, these two quantities coincides. So far, so good.
Yes.
So right now, we know how to integrate a bounded measurable function on a measurable set with finite measure. Okay. So from simple functions, we moved to bounded measurable functions. As I told you, at each stage, you should confirm that integration that you have defined verifies properties that you expect. For instance, linearity and so on. So that is the next thing what we are going to do for a bounded measurable function on a finite measurable set whose measure is finite. I will prove that the linearity holds. Okay. But before that, if you recall, these definitions were motivated by Riemann integration theory. Riemann integration is defined for bounded functions. Okay, we just replaced step functions with simple functions. Okay, so naturally, our expectation is that suppose the function that you started with, that is the bounded measurable function that you started with, happens to be Riemann integrable, suppose, then you can integrate it in Riemann sense and you will get a value. And now you have a new integration in this Lebesgue sense. And our expectation is that both should coincide. Okay, so that we are going to verify first. So let me state it as a proposition. Let f be a bounded function on AB, so that you can talk about Riemann integration. If f is Riemann integrable, then f is measurable. Once it is measurable, you can talk about now it is measurable, it is bounded, and it is on a bounded set. I mean, measurable set with finite measure. So you can talk also about level 1 Lebesgue integral. Okay. And the result says that integral a to b f of x dx, that is the usual Riemann integral, coincide with integral over the set AB f df. I mean the Lebesgue integration. So left side you have a Riemann integration and right side you have the Lebesgue integration. Both will coincide. Okay. Is the result clear?
Yes, sir.
Bounded function on an interval. So you can talk about Riemann integration. Suppose it happens to be Riemann integrable, then automatically it is measurable. So now you have a measurable bounded function. So you can talk about it Lebesgue integral, and the theorem says that, or the proposition says that both will coincide. Okay. Proof. It's very simple. The proof is based on the observations that every step function is a simple function. Note that every step function is a simple function. So now you please keep in mind how we defined the lower Riemann integral a to b f of x dx. How do you do that? You divide AB into several subintervals, and in each subinterval, you consider f of x to be a constant, and that constant value is infimum of f of x over that subinterval. Yes or no?
Yes, sir.
So this will be less than or equal to supremum of integral over phi dm, where phi is less than or equal to f. Do you agree?
Yes, sir.
Because lower integral a to b fx dx is obtained by approximating f of x in each subinterval with a constant, and that constant is infimum of f of x. That means instead of integrating f of x, you are integrating a particular step function. But this right hand side, what I have written is supremum over all the simple functions. Okay, so supremum will be less than or equal to one of that element in that set, and that is lower Riemann integral. And now phi is simple and phi is less than or equal to f. Now you consider psi simple and psi greater than or equal to f. So you have phi less than or equal to f less than or equal to psi. And you have proved in level 0 that if you have two simple function phi and psi, and phi is less than or equal to psi, integral over phi will be less than or equal to integral over psi. So this will be less than or equal to integral over psi dm, and this is true for any psi greater than or equal to f. Okay, and then hence it is true for infimum of all psi greater than or equal to f, psi simple. Here phi simple. Is that okay?
Yes.
Yes, sir.
Now, what is this? Infimum of psi greater than or equal to f, integral over psi dm. Can you say
Upper
that?
limit.
1 minute, 1 minute. Before that, can you say that this is less than or equal to integral a to b f of x dx upper Riemann? Because what is upper Riemann? You are approximating f of x in each subinterval with the supremum. That means instead of integrating f of x, you are integrating a step function which is greater than f of x. Is that okay?
Yes,
Yes.
sir.
While calculating upper Riemann integral, actually instead of integrating f of x, you are integrating a step function which is greater than or equal to f of x. But step functions are simple. Therefore, infimum taken over all simple function integrated will be less than or equal to one particular simple function integrated. And that one particular step function or simple function is the one which obtained by taking supremum. Okay, so this inequality follows. Now we know that f is Riemann integrable. Therefore, upper Riemann integral should coincide with lower Riemann integral since f is Riemann integrable. That means the inequality that I have written, the sequence of inequality that I have written, all should turn out to be an equality. Since f is Riemann integrable, integral a to b f dx upper is equal to lower integral a to b f dx. And therefore, the inequalities in star, are all equalities. And now you consider the second and third supremum integrated simple function where phi is simple less than or equal to f, and integration of simple functions greater than or equal to f taken over infimum, and both these things coincide. and that will give you that f is measurable by the theorem that we proved yesterday. Therefore, f is measurable. And further, the second quantity or the third quantity is what we call as integral of f dm. Okay? But they are equal. So integral of f dm Lebesgue AB is same as integral over a to b f of x dx. Riemann Lebesgue. So for a bounded measurable is not needed, bounded function on an interval, if it happens to be Riemann integral, automatically it happens to be measurable, so that you can talk about Lebesgue integral, and Lebesgue integral will coincide with the Riemann integral as we expect. Okay. The next proposition is again in the similar line as I told you. In each stage, you should see that the integral defined satisfies the linearity. Let f and g be, now we know only to integrate bounded measurable functions. F and g be bounded measurable function defined on a measurable set E with finite measure. M of E is less than infinity. Then integral over E AF plus BG dm will be equal to A times integral over E f dm plus B times integral over E g dm. Please note that similar result we know for what? Can you complete?
Riemann integration.
Riemann integral, you know, that's okay. That's not needed here.
Functions.
For the simple function,
Simple
for level 0, we know. For the level 0, we know. Now we may use it to do it for level 1 because the Lebesgue integral of f is defined via Lebesgue integral of simple function. Everything finally boiled down to simple function. Okay. Proof. So the main point of the proof is the following. If psi is a simple function, then a times psi will also be a simple function. If psi is a simple function, so is a psi. And conversely, if a psi is a simple function, psi is a simple function, provided a is non-zero. And conversely, a psi is a simple function, a not equal to 0 implies psi is a simple function. Keep this observation in mind. And now first let us tackle the case when a is greater than 0. Let a greater than 0 and let us consider integral over E AF dm. AF is the function which we want to integrate. Okay. Now, how do you integrate? Level 1 definition is instead of integrating AF, you have to integrate what?
Its canonical form.
Not canonical form. AF is not a simple function. Oh, I am bit and happy that despite several repetition, you are not getting how we are progressing. Level 0, we have defined integral of simple function. Using that level 0, now in level 1, we have defined integration of bounded measurable function. Okay. Now I am asking, how will you integrate a bounded measurable function AF? How do you integrate? Instead of integrating AF, I will integrate
Simple function.
simple functions greater than or equal to AF, and then I will take the infimum. Or you can take simple function less than or equal to AF and then take the supremum. Okay. So by definition, this is equal to infimum integral over E. Let us say psi tilde dm, where psi tilde is greater than or equal to AF, psi tilde simple. Do you agree?
Yes, sir.
So instead of integrating the given bounded measurable function, the definition says that you integrate the simple measurable function greater than it and then take the infimum. But now use this observation. Instead of taking the simple functions greater than or equal to AF, it is enough to take simple functions greater than or equal to F. Because all the simple functions greater than or equal to AF comes via simple functions greater than or equal to F. Because of this observation, psi is simple if and only if A psi is simple, when A is greater than 0. So I can write this as infimum of psi greater than or equal to F, psi simple integral over E, A psi df. Do you agree?
Yes, sir.
In order to get a simple function greater than or equal to AF, it is enough to take a simple function greater than or equal to F and multiply with A. That's what the observation shows. Okay. And now this is equal to A, I can pull out infimum psi greater than or equal to F, psi simple integral over E psi df. That is equal to A. Now what is this? You are integrating a simple function greater than or equal to F and then you are taking the infimum. By definition, what is it?
Integration of F.
Integration of F df. So integration of AF is same as A times integration of F. Okay, for A greater than 0. Now let A less than 0. A equal to 0 is trivial. A less than 0. Okay. Now integral over E AF df. Okay. In order to integrate a bounded measurable function, what you have to do is take a simple function, integrate greater than or equal to that function or less than or equal to that function, depending upon which you want, which approach you want. So here what I will do is I will consider a simple function less than or equal to AF. I will integrate it and then we'll take the supremum. But instead of worrying about simple function less than or equal to AF, it is enough to take simple function less than or equal to F. Okay. So this is equal to integral of A phi dm phi less than or equal to F, phi simple, and then take supremum. Okay. Now approach is same. So now you can pull A out because for simple functions you already proved this result. A times supremum over all phi simple, phi less than or equal to F, integral phi dm. And by definition, this supremum is integral over E F dm. Okay, so this proves that scaling result that integral of AF is 8 times integral of F. Now I have to define for the sum. If F and G are integrable, integral over EF plus G is integral over EF plus integral over EG. Now, for that, if I want to integrate F plus G, I should consider simple functions less than or equal to F plus G and integrate them and then take supremum. Or I have to consider simple function greater than or equal to F plus G, integrate it and then take infimum. Okay, keep that in mind. Now, if psi1 is a simple function such that psi1 greater than or equal to F and psi2 is a simple function such that psi2 greater than or equal to G, okay, then you can observe that psi1 plus psi2 will be again a simple function, is a simple function, and psi1 plus psi2 will be greater than or equal to F plus G. Okay, so now instead of integrating F plus G, which I don't know how to integrate, I will integrate psi1 plus psi2. Okay, integral over E F plus G dm. This is what I want. I am trying to estimate it using integral over E psi1 plus psi2 dm. Now tell me, what is the connection between these two? It is equal or less than or equal to or greater than or equal to?
Less than equal.
Less than equal to.
Why? Because by definition, integral over E F plus G is infimum of integral over all simple functions greater than or equal to F plus G. Psi1 plus psi2 is just one simple function. Okay, so this is less than or equal to. Do you agree?
Yes, sir.
Sir.
Now, for simple function, you already know that that is linear. So I can write this as integral over E psi1 dm plus integral over E psi2 dm. So this inequality is true. Ultimately, it is an inequality. This inequality is true for all simple functions psi1 greater than or equal to F and all simple functions psi2 greater than or equal to G. Yes or no?
Yes, sir.
Yes.
This inequality is true for all simple functions psi1 greater than or equal to F and all simple functions psi2 greater than or equal to G. Once it is true for all, it should be true for infimum. And therefore, taking infimum, taking infimum, integral over E F plus G dm, that's a constant. There is nothing to take infimum there, is less than or equal to take infimum over all psi1 and infimum over all psi2. What you will get?
Integration of F and integration of G.
Integral of F dm plus integral over E G dm. Do you agree? That's definition. That is how we integrate a bounded measurable function. Take integral of simple function and then take the infimum. Okay, simple function greater than. Is that okay?
Yes, sir.
Yes,
So
sir.
we proved inequality. That's not enough. We want equation. So can you guess what we will do to get the reverse inequality? Here we approached by simple functions greater than or equal to F. We can also approach by simple function
less than equals to F.
less than or
Less
equal
than
to.
equal.
On the other hand, if phi1 is a simple function, phi1 less than or equal to F, and phi2 is a simple function. Phi2 less than or equal to g. Phi1 plus phi2 is a simple function. And phi1 plus phi2 is less than or equal to f plus g. So now instead of integrating f plus g, which I don't know, I will integrate phi1 plus phi2. Okay. So integral over e phi1 plus phi2 dm and integral over e f plus g dm. How it is connected. Remember that by definition, integral over e f plus g dm will be you integrate all simple function less than or equal to f plus g and then take the supremum. Okay, so this is supremum of quantities that you are having here. So this will be what? Less than or equal to. Yes or no?
Yes.
Yes.
So I will write in
Yes.
the reverse way. Okay, I will write in the reverse way. I will write first integral over e f plus g. Therefore, integral over e f plus g dm, which by definition is supremum of integral over e all simple functions less than or equal to f plus g, will be greater than or equal to integral over e phi1 plus phi2 dm. Do you agree?
Yes, sir.
It is just a definition. Definition of integral of bounded simple function is supremum of integral of all simple function less than or equal to f plus g. Phi1 plus phi2 is just one such function. Okay. And for simple function, you know that it is integral over e f1 dm plus integral over e f2 dm. Okay. And now this is true for any simple function phi1 less than or equal to f and any simple function phi2 less than or equal to f. Okay. Therefore, it should be true for supremum. Now take supremum. Taking supremum. Supremum over what? Supremum over all functions phi1 less than or equal to f simple and all functions phi2 simple phi2 less than or equal to g. We will get integral over e f plus g dm is greater than or equal to integral over e f dm plus integral over e g dm. Okay, this is star 2. Now you can club by star 1 and star 2. Integral over e f plus g dm is equal to integral over e f dm plus integral over e g dm. You should understand and appreciate the process. So first we proved the result for simple functions. Now since non-negative, sorry, not non-negative, measurable bounded functions integral is achieved via simple function, we could prove it for measurable bounded function as well. The linearity we have proved. Okay. Now, let us go back and see once again level 0 and level 1. I am a bit worried that you are still not okay with how we are progressing. First, we have defined for non-negative simple function. Non-negativity is not a stringent condition. That is just to avoid infinity minus infinity type of things. So if that kind of issue does not arise, then we can define integral of any simple function, need not be non-negative. Okay, any simple function. Now in the next level, we went for a bounded measurable function. Okay, so simpleness condition we avoided, but there are some conditions like it should be bounded and it should be defined on a measurable set with finite measure. Okay, now I am going to level 2. Level 2. Okay. I will define integral of a non-negative measurable function, but defined on any measurable set. I don't mind whether measure is finite or not. If f is a non-negative measurable function, potentially f could be unbounded. I don't mind it. Defined on a measurable set E, then we define. How to define integral is the question. How to define integral over E f df. Compare and contrast. In level 1, you could integrate only bounded function. You could integrate over sets which are measurable with finite measure. Now here, potentially the function f could be unbounded. Potentially the set E could be of infinite measure. But we are putting a condition that f should be non-negative. Is that clear?
Yes, sir.
I have not
Yes,
defined. I will define. Okay. Now, while going from level 0 to level 1, we were knowing only integration of simple functions. Therefore, to define integral of a bounded measurable function, we made use of integral of simple functions. Is that clear?
Yes, sir.
Yes, sir.
But now moving from level 1 to level 2, now you not only know integration of simple function, you also know integration of
Bounded
Bounded function.
function.
bounded measurable
Measurable.
function over a
Bounded.
Measurable set of
Finite
finite
measure.
measure.
finite measure, over a set of finite measure. That I am going to use. Okay. So integral over E f dm, I will define as integral over E h dm. So I am estimating via h, and then I will make this estimate better and better. But before doing that, can you guess what would be this h?
Bounded and
Bounded measurable function. Okay, where h is less than or equal to f. Okay, where h is a bounded measurable function, not over. You don't know how to integrate a bounded measurable function if the set has
Finite measure.
infinite measure, but we don't know whether integral over E, that E will have infinite measure or not, we don't know. Okay, so how to tackle that issue such that H is a bounded measurable function such that measure of set of all x such that h of x not equal to 0 is finite. E may be of infinite measure, but we are worried about only those points where h of x is non-zero. That is of finite measure. So again, you can integrate integrate h over E. Okay, and do it for each h less than or equal to f. That will give you underestimates, because h is less than or equal to f. That is going to give you underestimate. Now what you will take? You will take
supremum.
supremum. That's it. That's the definition Lebesgue did. Okay. So now, knowing how to integrate a bounded measurables function over a set of finite measure, I can integrate a non-negative measurable function. I will leave to you where this non-negativity is used. You may not see it explicitly. You may think that why don't I define this for any function? Why this non-negativity? So please think over. Okay. And also, why only I am defining through supremum? Why don't through
Infimum.
infimum? By taking bounded measurable functions greater than or equal to f. Can I do that? So these two questions I am leaving to you. Okay. One is why I am not defining infimum of all bounded measurable functions greater than or equal to f. Why I am not taking that? And secondly, where is this non-negativity assumption coming into picture? Okay, explicitly you may not see it, but it is used. You think what happens if at some point f becomes negative. Okay, so level 0 is clear.
Yes.
Yes, sir.
What was that?
Integration of simple function.
Simple functions.
Simple.
Okay, level 1,
Integration of
Integration
bounded
of bounded
function on
bounded
finite
measurable function over a set
bound
of finite measure which
finite.
attacked via simple function. Now level 2, now we don't need boundedness. Potentially the function could be unbounded. We don't need measure of the set over which integration is done to be finite. But what we need is non-negative. Non-negative. Okay. And then you make use of available knowledge. Available knowledge is not now just integration of simple function. We know how to integrate bounded measurable function. Make use of that. Okay. Now let me make a note here. LHS is just a simple and RHS give you its definition. Do you see that this definition may give value to be infinity as well? You are taking supremum. That supremum could be
Infinite.
infinity.
Infinite.
Note that integral over E f dm in the above definition could be finite or infinite. Finite or infinite. If integral over E f dm is finite, then we say that f is integrable. F is integrable. So now we are having integrability of a non-negative function which can be unbounded over any set, whether it is of finite measure or not, we don't bother. If the integral happens to be finite, we call it as integrable. Okay. Another thing, if you closely observe, those who are curious will have this doubt. Consider level 0. In level 0, you integrated what?
Simple function.
Simple functions. Is it right?
Yes, sir.
Now, come to level 2. F could be any non-negative measurable function. In particular, it could be a simple function. F could be simple function. Then level 2 says that integral over E f dm will be supremum of all h less than or equal to f integral over E h dm, where h is a bounded measurable function with all these conditions. So apparently there are two different definitions for integral of a non-negative simple function. Yes or no?
Yes, sir.
One by level 0 and another by level 2 by using supremum and so on. So in appearance, it looks that for a non-negative simple function, you can define integral in two ways, one using level 0 and one using level 2, but both will give you the same value. Okay, I will not prove it. Maybe I will reserve it for a tutorial, but let me remark it. If phi is a non-negative simple function, we have apparently two definitions. We have apparently two definitions for integral of phi dm. See level 0 and level 2. But both coincides. I will keep this as one problem in tutorial sheets. Okay. So there is no ambiguity. Okay. So what is our progress? We could integrate now any non-negative function, measurable function. We don't need boundedness. We don't need the set over which we are integrating to be a finite measure. Okay. Now in this stage also, you should convince that it satisfies, the definition satisfy all the properties that we expect. For instance, linearity. Okay. So let me make it as a proposition. I will not prove it. Why I don't want to prove it? Because it follows from the definition. Let f and g be two measurable functions, non-negative measurable functions. Then I know how to integrate them. I don't know whether f and g are bounded, but integral over e f plus g I know how to define. Dm will be equal to integral over e f dm plus integral over e g dm. Similarly, integral over e cf dm will be equal to c times integral over f dm for all c greater than 0. Because now we are integrating only non-negative function. Do you see that it will follow directly? You see how you have defined integral of f? It is using
Bounded
H.
measurable function.
integral over h, where h is a bounded measurable function. And for that case, you already proved this proposition we already proved. Today we proved. Use that, you will get it. Okay. So I don't want to do the same exercise again. Now, on the contrary, I want to finish this hierarchy by defining level 3. Simple. Next, bounded measurable functions over a finite measure set. And third, non-negative, but need not be bounded, need not be over. But there is a condition, non-negative. That I want to avoid. Now we want to avoid that. Okay. Suppose f is a measurable function. Could be positive and negative at some points. Measurable function. Now you know how to integrate positive function. Non-negative function, how to integrate, you know. I will make use of it. Okay. Define functions f plus and f minus as follows. F plus of x. How do I define? It will be same as f of x if f of x is greater than or equal to 0, and it will be 0 if f of x is less than 0. This can be considered as the positive part of f of x, and it is actually maximum of f of x comma 0. At each point, you compare f of x and 0 and take the maximum. That is f plus x. Okay. Similarly, define f minus x as, you can guess now, 0 if fx is less than 0 and minus fx if fx is greater than 0. Did I make some mistake? Can you tell me how to define f minus? Again, I want f minus also to be non-negative. Yes. So what I want is actually
minus f of x square.
maximum of, let me tell you, minus fx 0. This is what I want. Maximum of minus fx 0. So that again it will be
So 0 for fx positive and minus
fx positive.
No, sir. 0 is fx negative, minus fx is fx.
No, I told you, no,
Fx
I want
negative.
finally f minus x to be positive only. So I think this should be greater than. This
Yes,
should
sir.
be greater than, and this should be less than. Equal to I can include anywhere. That doesn't matter. Okay. I want finally f plus and f minus both to be non-negative. This is the definition. Maximum of fx 0 and maximum of minus fx 0. F plus and f minus. These are called positive and negative part. And one thing that you can observe is the following. This is the important fact. Note that f you can write in terms of f plus and f minus. F is equal to, can you tell me how to write f? How to decompose f in terms of f plus and f minus? No? Is it that difficult?
Plus minus f minus.
F plus minus f minus. And you can also see that modulus of f, right now we don't want it, but anyway, f plus f minus. So a given function you have decomposed into two functions and both of these functions are non-negative. Now, do you know how to integrate a non-negative measurable function?
Yes, sir.
Level 2. Level 2 tell how to integrate a non-negative measurable function. So now you can expect how we will be defining integral over E f d. How will you define integral over E f dm? Any guess? Integral over E f plus minus integral over E
F minus.
f minus. Okay.
F minus.
Now again a question is, what happens if it is both are infinity? Infinity minus infinity, there will be an issue. Okay. How to handle that? So before that, let me make a comment here. This decomposition, especially the first decomposition, this decomposition, give me 5 more minutes, allows us to define integration, or we can write this decomposition allows us to extend the definition. Extend the definition of integral. Definition of integral to a measurable function which may be both positive and negative. Measurable function which takes both positive and negative value. There is no condition now, like it should be non-negative and so on. So this decomposition is very innocent, but it gives us a lot of things. Now the definition. A measurable function f is said to be integrable, over E. Integrable over E if integral over E f plus and integral over E f minus are both finite. In other words, both f plus and f minus are integrable. That's how we define integrability in level 2. A non-negative measurable function is said to be integrable if its integral is finite. Okay, f plus and f minus both are non-negative, so they are said to be integrable if the integral of them are finite, and in that case we will call f to be integrable. Both are finite, and in that case, we define integral over E f dm. This is the definition. Now I can integrate any function, need not be non-negative and so on. As you expect, the definition would be integral over E f plus dm minus integral over E f minus dm. There is no question of infinity minus infinity now. We already imposed the condition f is integrable. Only when it is integrable, we will integrate. Is that clear?
Yes.
Yes, sir.
Now you please give some time and slowly read level 0 to level 3 and understand and appreciate the Lebesgue approach. Starting from simple function to non-negative measurable function via bounded measurable functions, and then from non-negative he went to any function by decomposing into 2 and so on. Okay. And for this decomposition to 2 and then defining integral to be the parts of each and so on, we are verifying that at each stage it is linear. Integral of AF plus BG is equal to A times integral F plus B times integral G. We are verifying at each stage. Okay. I will stop with maybe one example, or more specifically a non-example. That means which is not integrable. Let F from R to R, I will be quick here, and let me define f of x to be this. F of x is equal to 1 when x greater than or equal to 0 and minus 1 when x less than 0. As you know, you cannot talk about Riemann integration over entire R. Riemann integration is only over a bounded interval. Okay. So now I wanted to see whether integral f dm R makes sense or not in the Lebesgue sense. Okay, and I claim that it is not defined, because if you want integral over R f dm, I want integral over R f plus dm and integral over R f minus dm both to be finite. Okay, because here you will get, you check it, integral over R f plus dm is also infinity, and integral over R f minus dm is also infinity. So we will not attempt to define Lebesgue integral. We just say that f is not integrable. Okay. Is that clear?
Yes, yes, sir.
Yes.
Now in the next stage, what we are going to do is, first we will verify that in level 3 also linearity holds. That means whenever f and g are integrable, integral over E AF plus BG is equal to A times integral over F plus B times integral over G. That we will prove. Having defined integral for any measurable function, we have completed the definition. Now the question is, why we wanted Lebesgue integration was there are some shortcomings for
Riemann integration.
Riemann integration. Especially Riemann integration does not behave well with the limiting process. Each fn is Riemann integrable. Fnx converges to f of x. You may not be able to say that the limit function will be Riemann integrable. Even if that is the case, you may not be able to interchange the limit and integration. So a natural question is whether Lebesgue integrations overcomes all these issues. whether Lebesgue integration behaves well with limiting process. That means Fn converges to F. Each Fn is Lebesgue integrable. Can we talk about Lebesgue integrability of F? If that is the case, whether integral of F will coincide with limit of integral of Fn. Those are called limit theorems. That is our next target. Okay. What we completed is definition of Lebesgue integral. Starting from the very elementary stage, simple function, we went up to any measurable function. Now you can integrate. I mean, at least you can talk about the integral, or you can say that it is not integrable. Is that clear?
Yes.
So
Yes,
I
sir.
had a doubt in
Next.
remark of level 2.
Remark of level 2. Yes, tell me.
So how can we say there are two definitions? We have defined level 2 using level 0. If there is no level 0, there is no level 1. If there is no level 1, there is no level 2.
That's okay. Now please listen. That's what I'm saying. Apparently there are two definitions, because one is like, see, remember, for first level 0, you need only the expression for phi. Yes or no?
Yes, sir.
Canonical expression or whatever it is. But if you approach through level 2, what you are doing is you are collecting all simple functions h less than or equal to f. You are integrating that simple function. While integrating that simple function, you will use level 0. That is okay. But you are defining it through a supremum.
Yes, sir.
Instead of integrating with a single step by summation alpha I m of ei, what you are doing is you are doing it for each function h, and then you are taking a supremum. Is that clear?
Yes, sir.
What's the guarantee that that supremum taken over all simple functions and level 0, one single structure definition, both will coincide? That's what I am saying. That is what I am asking.
Yes, sir. Okay, sir.
Okay, I'm not saying that, of course, while defining level 2, level 0 is used. That is okay. But level 0 gives you a single step evaluation, whereas level 2 gives you evaluation via integral of many other functions. Are you getting my point?
Yes, sir.
But what is the guarantee that both will coincide? That need to be checked. Otherwise, everything got a mess. Anyway, that we will include as a tutorial problem and do it. Okay, so I think I will stop here. You have a class.
Sir, when will we get the graded sheets?
I am done almost. Maybe Monday you can get. Okay, but I should say that I am really disappointed. Even the questions like prove that it is a sigma algebra generated by is not doable means it's a common theme in mathematics. When you say it is something smallest, say it is the smallest sigma algebra, first you have to verify that it is a sigma algebra, and then you have to verify that if there is another sigma algebra, then that this sigma algebra is contained in that. Second step nobody is doing. I mean, mostly students are just stopping with it is a sigma algebra. It is a sigma algebra doesn't mean that it is a sigma algebra generated by that. So like that, many questions which are doable, people are not, I don't know where we are missing. Anyway, I need a discussion that tutorial class I will use. And in fact, I should say that there was a typo in one question. Those things I will discuss. By Monday, you can get it. I think I have answered your question. Thank you.
Thank you, sir.